All right, so welcome everybody to the latest GBO Science Lunch Talk. Today we have with us Merel Hoff, who is joining us from University of Michigan or nearby. And today she'll be talking about planet-forming disks. So when you're ready, Merel, take it away.
Okay, let's get this started. Okay, thank you so much for the introduction and also for the invitation to be here to give this talk today. So yeah, I'll be talking about planet-forming disks, also a little bit about slightly earlier systems. But to start with the main motivation behind this work, I will show a little bit of the big picture. So these days we are able to observe both planetary atmospheres as well as their formation environments, these disks, in a lot of detail. And JBOC that's coming up will provide even more, I think, especially in the planet atmosphere side. So we are now at a position to start addressing whether and how these planets are connected to their formation environment. So for example, can we connect their bulk composition that we see in the atmosphere to maybe a specific location in the disk to narrow down how and where these planets form. And maybe if we think about habitability, are we able to connect more specific molecules, for example, water, that we see in planets to maybe to their formation environment to learn more about how an Earth-like planet and maybe life might form. So just to get us all on the same page about some of the terminology that I'll be using. So we know that stars form when these dense cores and molecular clouds collapse, and the density becomes high enough, we form a protostar. And to conserve the angular momentum of this rotating infalling material, we form a disk around the star launches an outflow. And over time, this envelope material dissipates. We end up with a pre-main sequence star surrounded by a disk. This disk contains gas and dust, and that's material that eventually form the planets. And then we end up with planetary systems like our own solar system. And initially, we thought that these planets started to form in these mature, fully grown disks, and therefore we've called them protoplanetary disks. I'll come back to this later because now it seems that it already starts much earlier, and these disks are still embedded in their envelope. So based on the spectral energy distribution, we call these protoplanetary disks also class 2 disks, and these embedded disks class 0 when the envelope is still dominating, and class 1 when there are probably more involved and the disk and the stellar mass are dominating. Throughout my talk, I also refer to these systems often as young disks when they're still embedded, and more mature disks when they don't have envelope anymore. So from a perspective, if you think about where the material from our planets comes from, if it's just a disk, or whether, especially in terms of molecules, are they already formed earlier on and survive throughout all these stages onto planets, or maybe they have to be formed in earlier stages. It's always interesting to start with our own solar system first and see what we know from our own solar system. So this is a very complicated figure. I'm going to walk you through it briefly, and then I will just focus on the main result. So this is showing the abundance of elements in Earth mantle with respect to their abundance in a certain type of chondrites, which we think are like the most primitive material that we can see in our solar system as function of their condensation temperature. So this is the temperature at which half of this material is still in the gas phase and half is already in solids. And this trend that we're seeing, especially for those blue elements, has been interpreted as the fact that early on, before the sun formed and the planets formed, the material was heated to temperatures above 2000 Kelvin, completely atomizing all this material. And then during the formation of the disk, the material cooled down, and these materials condensed into minerals according to their condensation temperature. So the main point from this complicated figure is basically that this suggests that there has happened some sort of reset between the cloud stage and the disk phase. And so all, especially the refractory materials, had been evaporized and then formed back into refractory material. But if we look at more volatile material, for example, water, we see something different. So what people often look at is the amount of deuteration in water, so the D/H ratio, because this is a good probe of when water formed, or more specifically under what conditions the water formed. And deuteration is especially enhanced under cold conditions. So this orange bar shows the D/H ratio of water in interstellar material. And as you can see, most of the inner solar system bodies that we have measurements for, they show comparable values. And importantly, they're all enhanced with respect to the general D/H ratio in the protosun. And if you model this chemically, you cannot get this enhancement in the D/H ratio in water just by chemistry during the disk phase. But this must have formed in the earlier colder stages, and hence some form of inheritance of this water must have happened into the inner solar system. Another evidence of inheritance comes when we compare molecular abundances in comets, in this case, comet 67P, with abundances around a protostar. And this protostar is often considered as a protosolar analog. And this plot shows the correlation between these abundances, and you can see that they fall roughly on this 1-to-1 correlation. Again, suggesting that at least some of the material gets inherited from the protostellar envelope onto bodies. So the picture is pretty complex, and it seems that both reset and inheritance play a role, maybe differently so for different types of material. And if we think about this inheritance more, there's one long-standing problem with the composition of our own Earth, and it's that it's very low in carbon compared to the sun. So I'm going to talk about it a little bit more. And here I'm going to show the carbon to silicate ratio for solar system bodies with respect to the sun. So generally in comets, we find very similar carbon to silicate ratios as our sun. But if we look at the bulk silicate Earth, it's 4 orders of magnitude lower than what we see in the sun. So there is some uncertainty for the total value of Earth because we don't know exactly what's happening in the core. But even with a very generous upper limit, it's still 2 orders of magnitude below solar. And we see very similar values in different types of meteorites, and this is a lower limit for Venus. So what this plot is showing is that these inner solar system bodies have at least 2 orders of magnitude depletion in their carbon content with respect to the sun. And outer solar system bodies, so for example, comets that we expected to they formed in the outer region of the disk, they have solar values. So this suggests that carbon-rich grains must have been destroyed in the inner solar system, so where the Earth and these meteorites formed, such that carbon was present in the gas phase in those regions and could not have been sequestered by these rocky bodies. So we can put several constraints on the mechanism that should be responsible for this. So first of all, it should leave silicates intact because we don't see depletion in silicons, and there should be some solid material to form from these rocky planets. And a second constraint is that this process must happen early, before and maybe during the onset of the formation of planetesimals. So bodies like up to maybe starting from meter size. And that's simply because it's much easier to destroy like millimeter, centimeter sized particles than it is to completely destroy much larger bodies. So that raises the question, when is this period? When do planetesimals start to form? And like I said before, initially we thought that planet formation would start in these protoplanetary disks when the disk had fully formed. But I'm going to show a couple of recent results indicating that it might happen probably already earlier. Again, starting with our own solar system, there's evidence that Mars reached about half its size in less than 2 million years. So we think these disks seem to be at least 1 million years old. So either Mars should happen, should form very, very fast, or it should happen, or it should start early on. Similar for Jupiter, we see a dichotomy in meteorite composition. So details are not very important here, but this is one of the explanations for this, is that Jupiter's core formed very early, and therefore it prevented this material from the outer solar system to mix with material in the inner solar system. And to get the right compositions, it needs to happen within 1 million years. Although there were some very recent studies that could reproduce they could reproduce this meteorite dichotomy without forming Jupiter very early on. So this is still up to debate, I think. But also, if you look at the mass available in disk and compare it to the mass that we see in exoplanet systems, it hints to an early planet formation. So these dots are showing the mass in solids in exoplanet systems, and these lines are the median masses that we see in disks. So this bottom line is the median mass of these class 2 protoplanetary disks, and you can see that it's lower than like the majority of the exoplanet system that we see. So this suggests that these disks, that we don't observe the amount of mass necessary to form planetary systems that we see. In contrast, for younger disks, the mass is much higher, and it overlaps much more with the planet population that we see. So this is interpreted by that grain growth already starts in these younger disks, and by the time that we are in these protoplanetary disks, a lot of the mass has grown to sizes that we cannot observe anymore at submillimeter wavelengths. So a final example is this famous HL tau image. So this is a young embedded disk, and we see these rings in the dust. And one very exciting explanation of these rings is that it's carved by forming planets. So if that would be the case, then that means that this happens already early on because HL tau is still embedded. And this is a recent example of an even younger disk where we already start to see these rings. So again, suggesting that if these are signposts of planet formation happens very early on. So getting back to our carbon problem, if we have to destroy these grains early on before they have formed to larger sizes, it should happen during the protostellar phase. So maybe in the inner envelope, or maybe in a very young disk that has just started to form. In the literature, several mechanisms have been suggested for destroying carbon grains. For example, oxidation with OH molecules in the midplane, or oxidation with atomic oxygen in the surface layers, photolysis with UV photons. But so far, all the models show that none of these processes are efficient enough to deplete the carbon to the level that we would need to explain the level that we see in Earth. So I'm going to talk about a different process, and that's the thermal sublimation of these grains at the so-called soot line. So temperatures about roughly 300 or 450 Kelvin. And I'm going to focus on what kind of chemical signatures we would expect if this process is actually happening, and whether we see those signatures. So this is a schematic overview of the inner region of a protostellar envelope. So for simplicity, I'm not drawing in any disk. And this is the water snow line. So the water snow line is roughly at 100 Kelvin, and outside of the snow line, water, but also most complex organic molecules, they will be present in ice. While inside the snow line, the temperature is high enough to thermally desorb these molecules into the gas phase. And that means that inside this region, we can actually observe them. So similarly, we have this soot line in envelopes roughly at 300 Kelvin. So inside this soot line, we expect these carbon grains to thermally just sublimate into smaller pieces. And therefore, we expect a release of carbon, but also of nitrogen into the gas phase. Based on meteorite composition, we expect also that there is a lot of nitrogen in this refractory material that will be released. Most importantly, there won't be any oxygen, because this traditional so-called bottom-up chemistry that we have in the envelope and in earlier stages, which start from atoms and build them up either in the gas or in the ice into more complex molecules, this process locks up oxygen in water and CO. And this is very efficient, and it's very hard to get oxygen out of these molecules again. So the majority of oxygen will be locked up here, and an important part of oxygen will be present in silicate grains, but not in this carbon grain material. So that means that we get a top-down component of the chemistry in this inner region that just starts from the destruction of something larger and then gives you smaller components. And critically, it will be hydrogen, carbon, and nitrogen. And in models of protoplanetary disks, where you add a lot of carbon to the chemistry, we see that you then mainly form hydrocarbons and nitriles, so molecules like HCN and CH3CN. So we expect, therefore, an enhancement of these hydrocarbons and nitriles, and maybe even more complex nitrogen-bearing molecules inside the Snowline. And since this inner region is warmer, we might expect those nitrogen-bearing molecules to have higher excitation temperatures than oxygen-bearing molecules, which will be more uniformly present out to the water Snowline, so also more present in colder regions. So then the question is, since protostars have been studied quite well, do we see any of those two signatures in the current literature? So we definitely see evidence that oxygen-bearing molecules and nitrogen-bearing molecules have different spatial distributions. And I think the most well-known example is Orion KL, where we see most of the oxygen-bearing molecules over here, and what's called the compact ridge, while most of the nitrogen-bearing molecules are peaking here toward the hot core. So it's not completely uniform, because recent observations show some oxygen-bearing molecules peaking towards the hot core. So it's not fully understood what's going on here yet. And this is another more recent example of a high mass protostar. So the green contours show the dust emission. And you can see here those 4 oxygen-bearing molecules in the color scale. They all peak offset from the continuum peak, while these nitrogen-bearing molecules are all centrally compact. So we definitely see spatial differences between oxygen and nitrogen-bearing molecules, but not unambiguously and not in all sources. And the same is true when we look at the excitation temperature. So this is a complicated figure that I'm going to walk you through in steps. So this is showing an overview from the literature of measured excitation temperatures from observations for nitrogen and oxygen-bearing molecules. So each point in this figure is a source that has been studied in one particular study. So if a source has been studied multiple times, it will occur as multiple points in this figure. And then I'm showing the highest excitation temperature among all nitrogen-bearing molecules for that source in that particular study versus the highest temperature among all oxygen-bearing molecules. So the key thing here is that from carbon grain sublimation, we expect nitrogen-bearing molecules to be warmer than oxygen-bearing molecules. So we would expect all the points to lie in this upper part of the plot. And while we do see that about 40% of the points are in that region, with some examples that would even fall outside of the plot. Also, half of the points is in the other region. So there's no clear signature that nitrogen-bearing molecules are always warmer than oxygen-bearing molecules. There might be several reasons for this, not necessarily that carbon grain sublimation is not happening. And one of the reasons might be difference in observational settings between all these studies. So this is not one systematic study. This is just a compilation of everything that I could find in the literature that had measured both oxygen and nitrogen-bearing molecules. So they've been taken with different telescopes, hence different spatial resolution. And that would mean that you trace different physical regions in these envelopes. So some observations might be more sensitive to this hot inner region, while lower resolution observations might be more sensitive to colder material. And we're all comparing this in one figure. Also, different studies study different molecules, and we don't know, maybe some molecules are better tracers of this process than others. And maybe even more important, different studies, even if they target the same molecules, they might target different lines, and different molecular lines are sensitive to different temperatures. So that might create a spread as well. So what we would need is a uniform study of a large number of sources to narrow that down. And this is just one example of Orion KL and the different studies that have been done. And you can see that there's quite a difference in results just for this one source, with some results showing the nitrogen-bearing molecules much warmer, especially this result, but there's also where this evidence is much less strong. So a second reason for this scatter could be more physically related to the protostars that we're looking at themselves. And it could be related to so-called protostellar outbursts. So we expect these protostars to not accrete in a uniform fashion, but instead have these bursts of accretion. And this affects the temperature structure, but also the chemical structure in their envelopes. So this is again the figure that I showed before with our soot line. Inside we have the carbon grains destroyed and the nitrogen-bearing molecules enhanced. And then we have the water snow line. So this is the pre-burst situation. But then if this star undergoes a burst, it becomes much more luminous. It heats up the material surrounding it. And that means that it shifts these temperature contours, so the snow lines and the soot line, outward. So that means that we would have a much larger region where we expect nitrogen-bearing molecules to be enhanced. So we don't know exactly how long this burst phase lasts, probably less than 100 years. So catching a star during this phase will be hard, but it will be a phase where carbon grain sublimation might be easy to recognize just because this inner region is much larger and we can easily observe it. But then after the burst, the star goes back to its normal luminosity and the temperature of the material reacts almost instantaneously, but the chemistry and especially the freeze out needs some time to catch up as well. So that means that the soot line and the snow line, they shift back to their original location, but these molecules that were released from the grains during the burst, they'll need some time to freeze back out. So they will stay in the gas phase, even though the temperature would suggest that they need to be frozen out. So in this case, we might still see a spatial difference between nitrogen and oxygen-bearing molecules, but the temperature signature might be much harder to see because nitrogen is now enhanced outside of the soot line, so in a much colder region. And then finally, when the chemistry has caught up and these molecules outside of the snow line have frozen out again, it just depends on the strength of the burst, how well we can differentiate between oxygen and nitrogen-bearing molecules. So in the example that I'm showing here, the soot line shifted outward just inside of the quiescent water snow line location, and there will now be a very small spatial difference between oxygen and nitrogen-bearing molecules. And if the burst would have been even stronger, the soot line might have surpassed the water snow line, and there would have been no difference anymore at all because everything outside the water snow line would be frozen out, whether it's oxygen or nitrogen bearing. So I know this is a pretty complicated picture, but just the message to take away here is that some of the scatter that we see when we look at these excitation temperatures might just be because we're looking at protostars during different phases of their accretion process. And yeah, if we want to disentangle those two effects, we would have to understand and know which of the protostars are in burst and how to recognize that. So therefore, I want to continue a little bit more about protostellar accretion bursts and how we can observe it. So I'm going to continue with this type of cartoon and now a little bit more zoomed out. So this inner circle is now going to be the water snow line. And this dashed circle outside at lower temperatures is going to be the CO snow line. So CO freezes out at much lower temperatures, so it's present in a much larger region. So this is where we see CO in the gas phase, and then this inner region is where we see water in the gas phase. And if the star hasn't undergone a recent burst, this chemical signature, so the region where we see water and where we see CO, will match with the temperature profile that we expect based on the star's luminosity. And just because these snow lines are just basically temperature contours. However, if we had a recent burst, like I showed before, during the burst, the snow lines shift outward, and then after the burst, they will shift back in, but the freeze out needs some time. So if we have a recent burst, we will see that the chemical structure does not match with the temperature profile that we expect based on the luminosity. So basically we see water and CO out to much larger radii than we would expect from the luminosity. And people have been observing this mainly using CO, because this is the most easy to observe, because the CO snow line is at larger distances than the water snow line. And these are some results. So this is showing the radius out to which the CO extends as a function of the protostar luminosity. And this red line is basically this no burst scenario where we see the CO out to the CO snow line where we would expect it to be. And then we can see that the majority of these points are actually in a different region of the plot, which would correspond with the second scenario, where the CO is actually out to much larger radii than we would expect based on the temperature. So this suggests that many protostars have indeed recently undergone an accretion burst. So this was only looking at CO, and there's a reason why we would also want to look at water, and that is if we want to narrow down the time scale of these processes and narrow down when this burst actually happened. And this has to, and we can do this because, like I said, the freeze out needs time to catch up after the temperature goes back to normal. And water will catch up faster than CO, basically because the water snow line in this inner region, the density is higher. So water will freeze out faster than CO will after the burst. So that means we get two scenarios. So the scenario that I showed before, where both water and CO are more extended than we expect. And it must mean that the burst happened less than 1,000 years ago, because it will take water about 1,000 years to catch up. So if the burst had happened longer ago, water would have been back to what we expected in this second scenario. So in this case, we see water extending out to where we expect the snow line to be, but CO is still more extended. And CO takes about 10,000 years to catch up. So that means that this burst would have happened between 1,000 and 10,000 years. So observing both CO and water will help us understand more of these details of this burst process. So we can observe water in these protostellar envelopes. Unfortunately, we don't have that many observations yet. Here I'm just showing a recent example that I am working on. This is the protostellar envelope B1C. I'm showing here in blue H218O emission, and here at high resolution HDO, so deuterated water, towards this protostar. And we can use this to derive the snowline location. So this is basically an overview of most of the protostars where we know the snowline location based on water observation. So I'm going to focus on these blue points first, and then we'll talk about the orange a little bit later. So in blue, I'm showing the radius of the water snowline, again as function of protostellar luminosity. So this is B1C again that I showed in the previous slide, and we derived the snowline at roughly 20 AU. And this solid line is where we roughly expect the snowline to be based on the luminosity. So it's slightly lower than we would expect, but definitely no sign of an accretion burst. We do see a sign of an accretion burst in the CO emission. So this suggests that for B1C, the burst happened between 1,000 and 10,000 years ago. So this is another source that we observed, B1BS. And again, the snowline matches quite well with the expected location. We don't have CO measurements of this source, so we don't know if there was a accretion burst a longer time ago, but definitely not within the past 1,000 years. In contrast to IRS 15398, where the water snowline is at a radius needed for luminosity more than 10 times as high as what we currently observe. So this source has undergone an accretion burst within the last 1,000 years. Another example is Iris 2A. Again, it matches quite well with where we expect the snowline to be. And this source, we expect that it is currently in burst because it has a luminosity of 60. solar luminosities. So this would be a good source to observe for the carbon grain destruction. So the second thing that I'm showing in this figure are these orange triangles, and that's the radius where the 813 CO+ molecule peaks. And the reason why I'm looking at 813 CO+ here is because 813 CO+ has been suggested to be a good tracer of the water snowline. So if you are not able to observe water and you still want to locate a snowline, 813 CO+ might be a good molecule to look at based on this very simple chemical argument. And that's because 8CO+, so that's its main isotopolog, will be destroyed by gas phase water. So as long as you have water in the gas phase, most of your 8CO+ will be destroyed. And then you need some CO in the gas phase to actually form it. So in terms of our snow lines, we would expect 8CO+ to be between the CO and the water snow line. So yeah, we don't need water in the gas phase, and we do need CO to observe it. And that's just what we also see in these observations of B1c, and we also saw it before for another protostar. But the 813 CO+ here is nicely surrounding the water emission. And I'm also showing even less abundant isotopolog 8C18O+, and that's surrounding it as well. And here you start to see that they peak, but you also can see in this plot that these 813O+ peaks are much outside of the water snow line, that we might need even less abundant isotopologs, and that this inner ring might be a better tracer. So one of the reasons that the 813O+ peak is not directly at the snow line is because of chemistry. If you do chemical modeling, you'll see that it is not exactly at the same location. The beam size might come into play as well. So there's a lot of factors that you have to take into account to narrow down the snowline radius from your 813 CO+. And since in these envelopes we can observe water directly, 813 CO+ might not be very useful to observe because it's not easier, but your analysis will be more difficult. However, if you want to look at these young disks and locate the snowline there, for example, to study accretion burst, but also because the water snowline is thought to be very important for the formation of planet itself. And of course, if we want to know if we have water available to incorporate in forming planets, we want to know where the snowline is. But in these young disks, it turned out that observing water itself is very hard. So these observations show noise, but if water would have been in the gas phase at the same levels as we see in the protostellar envelopes, we should have had very clear detections here. So here we might want to use 813 CO+ to do it. And so I looked at some archival observations of the young disk L1527 to see if we could say something. And I will go quickly over this because I see I'm running out of time. So this is a disk, it's edge on. Let me see, this is the major axis of the disk. And at a first glance, you would say, well, there is less emission in the center. So we're seeing the same thing as what we saw for these protostellar envelopes. But because these are disks which have a different physical structure, embedded in an envelope, it's much harder to interpret these observations. And in fact, we often look at these so-called PV diagrams. And this is basically taken along the major axis of the disk, and each point along the major axis, we take the spectrum. So each row in this figure is a spectrum taken at each spatial point. And the important thing here is that emission from the disk, we expect that at low angular offset, so close to the protostar, but at very high velocities, or at higher velocities than the envelope, because of the Keplerian rotation of the disk. And the contours here show C17O as a reference for the velocities that we might expect. And you can see that the 8CO+, and especially the 813 CO+, doesn't go up to that high velocity, so it doesn't traces the inner disk. But I did some radiative transfer modeling for this source, and it seems that the sensitivity of the current observations is just not high enough to trace the material in the inner disk. So we're probing only radii down to about 40 AU, while we expect the snow line at maybe 15 or less. So we might be able to use 8CO+ here, but we would need more sensitive observations, basically. So then briefly, I want to end by talking a little bit about the young disk chemical composition and how it compares to older disks. And I'll stay with snow lines. And in the disks, it will look roughly like this. where we have the water snowline at 100, 150 Kelvin, and then going outward, the CO snowline at 20 Kelvin. And this is important for composition because this radial freeze out of molecules will create radial gradients in the chemical composition. For example, if you look at the elemental CO ratio, this will change at the different snow lines because molecules will freeze out. And the CO ratio is something that we often use to compare the disk composition to planet compositions. So if we want to observe the snow line in disk, it's harder because CO is so abundant that we mostly get optically thick in this disk surface layer and we won't be able to see the midplane. So again, this is an example why we would need a chemical tracer. And for CO, N2H plus has been suggested to be a good tracer and based on the chemical argument that it's destroyed by gas phase CO. So as long as you have CO in the gas phase, you won't see any N2H plus and you need N2. So this is an early, very beautiful ALMA image of N2H plus in the disk TW Hydra. And so we have this N2H plus ring suggesting that we have the CO snow line just in the inner radius. Just as for HCO plus, there are some chemical things and also the physical structure of the source that you have to take into account to actually derive the snowline location. But in general, N2H plus is just a good tracer of cold material where CO is frozen out. And this is a recent gallery of some protoplanetary disks in N2H plus. And just the fact that we see so much N2H plus in these disks means that they have a lot of CO frozen out and they have a large cold outer region. So what about these younger disks? If that's where planet formation starts, are the conditions there the same? Or can we just take these compositions from protoplanetary disks as their initial composition? You might expect that they are not the same just because these younger disks have higher accretion rates. And this some modeling results showing the CO snowline location as function of accretion rate with basically young disks on this side and more mature disks on this side, showing that the CO snowline is a much larger radii if you have a high accretion rate. So we tested this observationally by observing 5 of these young disks in C17O. So these are just the images of the disks that we have. And I will focus on these 2 disks because we are seeing them edge on. And that means that we don't have the problem that I discussed before, why we need N2H plus. We don't have to look through these disk surface layers, but we see the midplane directly. So I'm going to compare these results with 2 models, a warm model where we have CO in the entire disk, and a cold model where we have CO frozen out in most of the disks, so except in the inner disk and the surface layers. CO will be in the ice. And this will be comparable to these protoplanetary disks. So these are the modeling results. For a warm model, we see CO in the entire disk. For a cold model, we see it's more compact and we start to see this V shape. So comparing to the observations, L1527 resembles the warm model very nicely. But this larger disk, IRS-04302, and we start to see this V shape, suggesting that CO is freezing out in this outermost region of the disk. So just compiling these results together and comparing it to the class 2 disks, plotting their luminosity versus their snowline location. And this is showing that for these class 2 disks, even though they have similar luminosities, these class 1 disks, so these young disks, have their snowline further out than these more evolved disks. So they're actually warmer. I will skip this and go to their conclusion. So coming back to the question that I posed in the beginning, how can we link these planets that we're now starting to understand better to their formation environment? For our own Earth, we see that carbon is very much reduced with respect to what we expect from the sun. This could be because these carbon grains get destroyed in the inner region of protostellar envelopes, maybe young disks. Signs of this process would be an enhancement of nitrogen-bearing molecules in this inner region and higher excitation temperatures for these molecules. So we do see some of these signs, but not unambiguously. So we would need more studies to do that. And we actually have an active GBT proposal that's active where we are looking for this Hoff gas around these young protostars, see if it's actually there, and also to see how the dust is actually affecting maybe some of the other observations. Another question here would be what the effect is of protostellar accretion bursts and how that influences the observations of these two effects. So when we look at snow lines, we can use them to study both these accretion bursts, but also more general, the chemical and physical structure of in particular young disks. For CO, we can use N2H+ as a tracer. And we see, most importantly, that there's no CO ice in the inner 100 AU of these young disks. In contrast to more mature protoplanetary disks, where we see the CO snow line at a few tenths of AU. Important question would be, when do these disks cool down? And in terms of inheritance of the material, this will be interesting because if the majority of complex molecules form from CO ice, if there's no CO ice during this embedded disk phase, and there are still complex organic molecules present, it would mean that they would have to be inherited from earlier stages. So for the water snow line, because water is very hard to observe in these young disks directly, we might be able to trace it with H13CO+. And an important question, where is the water snow line located? And what would be the duration in this water, so that we can link it again to what we see in Earth and how material gets inherited. So with that, I'll thank you and I'll take any questions.
All right, thank you very much, Merel. That was exciting, a lot of information. We only have a little bit of time before 1. So if anyone has some quick questions, also if people are willing to stay past the hour, I'm sure we can get a few more questions in. Well, as everyone's thinking, I had a question that I wanted to ask, so we have time. So I'm just wondering, with the observed, CO emission as compared to where you expect the snow lines to be, can you or have you used that information to determine properties of the accretion burst, aka the luminosity or the strength of the accretion process?
Yeah, so that's something that you can indeed kind of infer if you assume what luminosity you would need to get the CO to the radius that you're seeing it. So yeah, based on that, you can kind of infer what the burst would have been. Yeah.
Do you use any of that information for studying or better understanding the properties of the star?
So I have not yet, but it is something that we, if we know it a little bit better, might take into account when we look at these maybe different excitation temperatures or differences in distribution between oxygen and their nitrogen-bearing molecules. If we would know what like maybe a typical burst size would be, but I don't think we know that well yet. But yeah.
Okay. Okay. Any other questions? Please feel free to unmute yourselves. By all means, do not be shy. Really? No questions? You're such a quiet bunch today. All right. Well, if nobody feels like continuing to probe Merel for questions about these disks, I personally love chemistry. That's a big aspect of my work, but on the other end of stars. So I have, lots of questions for you, but I think for the sake of brevity, it's just past the hour, so we should wrap things up here. But again, if any of you do have more questions, you want to talk privately, please, you're welcome to get in touch with Merel. Her email address is in the messages that were sent out. So with that, thank you so much again for joining us, Merel. This was a lot of fun.
Thank you for having me.
Of course. And everyone else, tune in next week. We have our own GBO postdoc, Pedro Salas, giving a talk on his research. So Thank you and take care, everybody.